Okay, so welcome to this presentation, and my name is Iraklis Psaroudakis, and I will be presenting this presentation titled "The Building Blocks of Elasticsearch Massive Scalability," and a few words about me. So I'm a principal software engineer at Elastic. Previously, I worked at Oracle Labs on graph-based analytics, and I did my PhD at TPFL in Lausanne on scaling up analytics. And I took my electrical and computer engineering degree at the National Technical University in Athens. And in this presentation, we will talk first about what is Elastic as an organization, what is Elasticsearch, the solution that we'll be focusing on in this presentation, how it scales out with shards, the notion of shards, how distributed searches and aggregations are executed. Then we'll talk a little bit about shard recovery, the clustered state, what it is and how it helps maintain a cluster, and some more advanced notions of scalability, scaling with data streams, and with index lifecycle management. And we'll be finishing with the vision that we have of even more unparalleled scalability with stateless and serverless. Just as forewarning that this talk contains personal views and is not officially endorsed, hopefully nothing erroneous, but just as a warning. So let's begin a little bit about who and what is Elastic. So it's the search analytics company. As it says here, Elasticsearch helps everyone find answers that matter from all data in real time at scale. It was founded in 2012. It's a public traded company with a lot of employees around the world. What Elastic offers is a performance that delivers relevant results in real time. There are two out-of-the-box solutions that are offered. The first is Elastic Observability, which is used to basically store logs. It's used for application performance metrics and other such information that can get you insights and actionable insights. There is also Elastic Security, which is used for real-time detection and protection of your infrastructure. And there is also a build-your-own Elasticsearch solution for scalable search and analytics on your data. All these solutions are using some toolset, if I can say it like that, that we call the Elasticsearch Platform. And it's composed of tools such as ingestion, like being able to ingest data from different formats and different data sources seamlessly and easily. There are also artificial intelligence and machine learning and search tools, and also some visualization and automation tools, such as things to help you build reports to present the insights that you get through our solutions. And all this can run either on the public cloud, like Amazon AWS, GCP, or Microsoft Azure, in a hybrid infrastructure, or even on premise on your own hardware. It's trusted and used by many organizations and companies around the world, and here spanning a lot of different industries, and here are some popular ones. So let's go immediately now to the technical side and the most interesting part of the presentation, of course, and let's dive into what is Elasticsearch. Elasticsearch is a distributed, scalable, highly available, resilient search and analytics engine. It's free and it's open. You can find it on GitHub. And if you see the screenshot I have from dbengines.com here, it's one of the most popular databases out there. And actually that website categorizes also websites by their database, by their specialized database model. And you will see that it's actually the first and most popular search engine database out there. So one of the key things that it offers is flexibility, first of all. You can, due to its scalability, also you can, due to its scalability, also toggle it more for indexing or for querying time. You can toggle performance, and there are many settings that you can do. It's based on a popular open source library called Apache Lucene that we will see in a bit. And as a search database, it offers much more than just what you might be used to search with grep or SQL's like operator. It can offer things like ranked results, fuzzy matching for text, complex search expressions, spell correction, synonyms, phrasing, stemming, and also more advanced capabilities like time series, geospatial, machine learning, stuff like vector search, etc. So let's go to the basic core, which is Apache Lucene. This is like the library that we use internally. And let's see how the basic data structure works that gives us the capability to do search. And it's basically called an inverted index. As an example here, I have a database, a document database with just 2 documents that you can see here, the examples. And let's say that we want to be able to search terms that clients, users give us. What we do is we build the inverted index, which is basically a map from sorted tokens of the documents to the documents that contain these terms. And here are the sorted tokens, and you will see which documents contain them. So you can see, for example, that dog is contained only on document 1, while the word lazy is contained in both document 1 and 2. So if a client comes and says, I want to query the database for the terms lazy and dog, then you would return only document 1. Well, if they search for lazy or dog, you would return both of these documents. And this inverted index is more or less the basis of what a Lucene segment is, and gives us the capability to do searches very fast and efficiently. Now, Elasticsearch on top of Lucene has the notion of shards in order to be able to scale and have even more very increased performance. A shard in Elasticsearch, each of these document database is called an index, and it can consist of many shards. Each shard is composed of Lucene segments, such as those that we saw in the previous slide. And there are 2 kinds of shards. There are the primary shards, which are used to partition your data, your document store into multiple parts. And primary shards are the ones that receive the ingestion, the writes, the new documents that you do to this document store. And if you have more of them, you can imagine that you can increase your write performance. You can ingest many more documents. And there are also the replica shards, which are automatically synced copies of their primary shards. So if you, these are optional as well. So if you have a replica per primary, then it's automatically synced. And these are useful for reads, meaning searches. So if you have more replicas, you can imagine that you can have better read performance. This is a visualization of how this might look like. So imagine that you have an index for children books, and you start with 1 primary, P0, and this primary shard is composed of 3 Lucene segments as are visualized here. You can have 2 primary shards, so then this would be split into 2 parts, and the second part, P1, the second primary, will have other Lucene segments. And if you elect to have replica shards, then this would be, in this example, I depict 2 replica shards per primary shard. This would contain exactly the same data as their primary shards. Now, apart from these shards, primary shards and replica shards, increasing the performance of writes and reads on a single machine, these are very useful for scaling out to multiple machines for increasing further performance. If one machine is not enough, you can add many more in order to service your workload. And Elasticsearch does that also in a balanced manner. So as you add nodes, then it automatically tries to balance the shards across the machines in order to balance also your ingestion and querying workloads among those machines. Also, another good capability is that it doesn't collocate replicas so that there is fault tolerance. Like if one of the machines dies, then there is another replica or primary shards on another machine and your data is safe. So let's see that with a visualized example. Here I depict one node with a logs index and one primary shard. And imagine that you create a new index called products with two primary shards. They all stay on the same machine. If you add another machine, though, Elasticsearch will automatically balance the shards away. So P1 from products might go to node 2. And if you add a replica for the logs index, then it will put it on node 2 so that it's away from its counterpart P0 on node 1 for fault tolerance. Now, in this distributed environment with many nodes, let's see how searches and aggregations in the next slide work. So searches are executed in a two-phased approach. You send a query to one of the machines. That becomes the coordinating node for the search. And then it sends the query to the shards that can execute it locally. It gathers the results, the top K results with the scores of the documents that match the terms that you're searching for. It gathers them from the machines. It sorts them based on the score. It gets, again, the top K, which are basically the final real top K results, and returns them to the client. So let's see a visualized example. Here there are three nodes with a products index and the shards that are shown here. There are two primary shards, meaning the data is partitioned in two pieces and two replica shards. So if a query comes in that wants to get the top 5 products whose description has the word denim in it, in this example, it goes to node 2. Any of the nodes can receive the query. This becomes the coordinating node. Then this node sends this query to two shards, to the two parts. It can, for each part of the data, it can choose either the primary or the replica shard. In this case, it has chosen P0 and R1. They execute locally the query and get the two top 5 results. They get them back to node 2. It sorts them by the score and gets the top 5 out of them. Optionally, it might go back to the nodes to fetch more data for those documents if the user query requests more fields, for example, like identifiers or something, and finally returns the response to the client. Aggregations work in a similar manner. Aggregations are a different type of workload that basically slice, dice, and combine data to get insights from your data. So let's look at an example of this. Let's assume that you want to sum up the prices of all the products. So what happens is, again, let's say that node 2 gets the query. It will send it to the parts of the data to sum locally the prices. So node 1 and node 3 sum them up, send back the local results, the local sums to node 2, which calculates the final sum and sends it to the client. Right, and a final piece on shards. As I told you, replicas are useful for fault tolerance. So let's imagine this example when node 3 dies and it has the replica R1. Then what happens is that Elasticsearch detects that and will create a new replica from the primary shard. So your data is, again, safe. And if a machine dies that has a primary shard, then Elasticsearch will pick one of the other replicas to promote it to become the primary. Right, so that's all on shards, and I would like to continue to tell you about what is cluster state and why is it useful in a distributed cluster with many machines. So you might have the question how Elasticsearch knows which machines are part of the cluster and where each shard is located. And that is contained in some metadata information, which is called the cluster state. It's the core information on which machines are part of the cluster and where each piece of data is. This information is maintained by one elected master node out of the nodes of the cluster. And this master node is responsible for proposing updates to the cluster state based on events such as a node leaving or joining, or an index being created or deleted, and distributing that knowledge to the other nodes of the cluster. It also decides on data placements, things like also node health checks, but it's important to understand that this is not used for reading. It's not in the critical part of your reading and writing workloads. Now, in order to maintain that information, we have a consensus protocol that is used by a small set of what we call master eligible nodes, who are responsible for voting on the cluster state proposals and establishing them across the cluster, as long as a quorum of them is alive and agrees on them. And these master eligible nodes are also useful if the master itself dies, then one of them will pick up the responsibility of being the master. Let's see how that works with some visualized examples. So let's say that you start with a totally empty cluster with 3 nodes, as you see here. These are master eligible nodes, but none of them is yet the master. So when the cluster bootstraps, one of them, let's say in this example, node 1, proposes to become the master. What happens is that it creates this metadata information, the cluster state, version 1, because it's the first ever information about the cluster, with the information that node 1 is the master, and it sends it out to the other master eligible nodes. The other nodes will see that and will vote on the changes. Let's say the happy path that they vote yes, they send back the response to node 1. Node 1 gathers the responses and sees that it has a quorum, basically that the majority of the master eligible nodes voted yes, so it becomes the master, and sends it back to the other nodes in order to establish this cluster state version 1 as the information for the cluster, to which also the nodes acknowledge back, and we say that cluster state version 1 has been established. This play happens with every core information that changes in the cluster. So as another example, let's assume that a new node joins the cluster. Doesn't need to be now a master eligible node. It just wants to join the cluster in order to have data and execute queries or ingestion. So it will go to the master node and request to join the cluster. The master node, as we said, is responsible for these changes, so we'll create a new version of the cluster state, in version 2, with node 4 being a member of the cluster. It will send it to all of the machines. They will send back acknowledgements, including the yes votes from the master eligible nodes. So it will check that it has a quorum achieved. It will then send again to commit the new cluster state to all of the machines, which will respond back and will say that the new cluster state has been established. As another visualized example, fast forwarded, I don't show you now all these arrows. Let's say that we create an index with one primary shard, P0. The master node will select on which node it will place it. In this example, it places it on node 4, and it does that by creating a new cluster state, version 3, that it goes through this protocol that we just described to establish it across all of the nodes. Right. So now that we talked about the cluster state, I would like to talk a little bit more about some more advanced notions of scalability, scaling with data stream, and another component that we have, which is called the index lifecycle management. So data streams are a bit are very useful for type of data that we call append-only time series data. And these are a popular use case of data, especially for things like logs. So imagine that you want to gather all the logs that your applications or your infrastructure is emitting, and you just want to store them in order to analyze them or later analyze them. So these data are just appended. You don't really modify them, right? And as they get older, they might also become less relevant or less useful. So this is where data streams shine. Basically, data streams is a series of indexes, right? With the last one being the one where the new data is written, and that one, based on time or size, we roll it over to an older index. So here is a visualized example. This data stream holds logs. The last one, the orange one, is the one where the new ones go, and they're from today, right? And you will see two indices from yesterday and from the day before. And so every day a new index is created. And only the last one is the one that receives the new documents. This is also useful for searches because with these types of data, you might be more interested in searching the more recent data rather than data that is 1 year old, for example, right? So when you do a search, because we have this capability, in this example, we roll over every day. Let's say that you want to search only yesterday's and today's data. Then we'll send the query to just these two indices, today's and yesterday. We don't need to send it to the indices before that. So this is also a way to optimize search performance. Apart from that capability, though, data streams are also useful. Okay, I forgot this. Yes, but I said it. With another component that we have, which is called index lifecycle management, that gives you the capability to slowly and gradually move your older data of those data streams to cheaper infrastructure. Right, so it gives you the capability to have tiers of data nodes with different cost and performance characteristics. And here is a visual example again. This is a longer chain than the example I showed you. And the indices roll over from machines that are, we call hot and expensive, to slowly machines that are warm, cold, or frozen. And let me get into a little bit more detail to understand what that means. The hot tier has the most recent data and also has the index that receives the new documents. So in this tier, you have machines that are more beefy, like they have better processors, they're faster. They might have solid state disks, which are fast. And you might also select to have two replicas per shard, because you want to increase fault tolerance. You don't want to lose data if multiple machines die, for example. For slightly older data, you might elect for the warm tier, which, for example, might have only one replica, so a little bit less fault tolerance. It might have spinning disks, which are slower but cheaper, and cheaper machines with cheaper processors, for example. And as data gets even older, you might elect for the cold tier, which supports only read-only data. You cannot modify the data there. And what we do there is that we store the data on a cloud object store, like Amazon S3, for example. So that's used for fault tolerance. We don't have replicas in this tier. And we load those data into the disk of the machines as searchable snapshots. That's what we call them, because basically we load them from the object store. And we execute searches on that data. And for even older data, you might elect for the frozen tier, which is one of the cheapest solutions. And basically what this means is that the data is not wholly cached on the machines, but those searchable snapshots that are on the object store, we dynamically fetch chunks of data as searches need them. So we'll issue a search, and every now and then we will fetch chunks of data from the object store in order to service the query. That's about ILM, and I would like to finish with the vision that we have of even more unparalleled scalability with what we call stateless. What does it mean? And the new serverless concept that we have in mind. In order to understand why we're going into this future and vision, let's summarize a few of the challenges that we have so far based on what I showed you. So from the aspect of data management, a few disadvantages of the current model so far is, first of all, there is the cost of ingestion with CPU and storage. Why? Because we also need to keep multiple redundant copies, the replicas that we talked about for fault tolerance. And also, another disadvantage we have with the current model is that we share the CPU resources for both ingestion and searches, right? Because the same shards, the same machines can execute, can receive new documents, but also service the searches of the clients, right? So you need to size the hardware so that they fit either your ingestion or your search workload or both of them together. And in the aspect of ILM that I just described you with all these data tiers, the hot, the warm, the cold, and whatnot, it's complex many times to understand the cost and performance trade-offs of the different data tiers, like how to configure the machines in order to have maximized cost savings. And it also has the disadvantage that a lot of data movement happens from tier to tier as the indices roll over and become older. And this also has some propagation delay between the tiers. So that's why we came up with the stateless model, where basically we store the data not on disk, but our primary source is a cloud object store, like Amazon S3 or GCP or Azure. What that gives us is that, first of all, we separate the compute from storage. The storage is an object store. And we, instead of having all these tiers that I showed you with ILM, we just have two. The index tier, which has machines that receive the ingestion and your new documents, and also the search tier, which has the machines that execute your searches. And the good thing about having these two tiers is that they can scale independently. So they scale to service the workload, either the ingestion or the search workload that you have. And the good thing about storing data on object store is that it's good for resilience, it's limitless, right? And all this has some simpler administration. One good thing is that we don't need the replicas anymore, so we don't need CPU for that, neither storage. So this we have found could improve throughput performance, indexing throughput performance by up to 75%. Right, and all this, the stateless is a requirement for our grander vision of serverless, whereby basically as a client, as a user of Elastic, you won't need to care at all about dealing with machines as servers. We just give you the APIs that you can use with some library clients or with REST, and we take care of managing all the infrastructure and the machines. And that means that we offer auto-scaling, auto-healing. It's versionless in the sense that we upgrade the cluster. You don't need to care about that at all. And basically, you just need to do your ingestion and your searches, and you don't need to care about much more for the infrastructure. Just to give you a sneak peek of how that looks like, here is a small video of how it looks like when you create a project on serverless. Let's wait for the beginning. Right, you select your library, you install the client. Okay, you create an API key which is used for connecting to your project. You copy your connection details along with that key. You configure your client, and basically you're ready to do ingestion and searches. Right. So in summary, Elasticsearch is an unparalleled scalable search and analytics engine, and we saw how it scales using instances and segments with multiple shards, and how it uses them in order to scale out to multiple machines. We saw how distributed searches and aggregations are executed, how a master node directs the cluster state updates across the cluster. We also saw how time-based append-only data streams are scaled with index lifecycle management, and how the future of serverless offers even more unparalleled scalability. And here are just some public examples of scalability that I could find, and some blog posts that might be useful for the interested viewer here. I would like to close with saying that we also have a very vibrant community that you can join and participate. We have a community portal, Slack, videos, discussion forums. We have a contributor program. We have newsletters where you can find news, for example, for artificial intelligence and machine learning. We have Elasticsearch Labs, where you can find things like integrating your searches with Chat GPT. Kariera's website, of course, and we also have a meetup also for Greece that you can join to see the next event. That's it for me, and I think I have a bit of time to get any questions. Thank you very much. Right, so I don't see something on the chat, but if you have anything, feel free to shoot a question. If not, that's where you will find me here at my website and find contact details to ask me anything.